Okay, so motion. Um, when we were in grade 7, we started to look at distance time graph. So this would be meters, and this would maybe be seconds or kilometers and hours. And I've got a y-axis, my y-axis, and my x-axis. And when I put them over each other, meters per second, in algebra we've learned to say this, meters per second. What is this? Well, it's speed. Is meters per second. How fast am I going? But where does speed come from? Speed comes from our distance time graph. Distance over time. So if I'm walking to the shops and I cover a certain distance, and then I stop because I see some blue cranes. That's our national bird. I see some blue cranes and I stop, but time never stops. So I look at them for a little while. Then I go, ooh, I'm a little bit late because I was watching these beautiful birds on the side of a stream or something. So I go a little bit quicker. And then I get to the shops, and although my garment says I'm doing lots and lots of steps, I'm actually sitting in the same, going around and round in circles down the aisles of the shop. Then, and these are specific times, and we can guess what those times are. And maybe I spend 30 minutes at the shop, and then I make my way home, and I don't stop anywhere, and I kind of do this. Okay. Now, what happened between here and here? And from grade 7, we learned that this and this, can you see the steepness of the slope? The steepness of the slope. The steepness of the slope tells us something. If it took me, say for instance, this was 2 kilometers, and say for instance, this is at 4 kilometers. If it took me, I want to be realistic and say, if it took me 20 minutes to do 2 kilometers over here, and then I did nothing, so maybe 20 minutes, and then from here to do another 2 kilometers took me 15 minutes. 15 minutes. What would you say was happening to my meters per second? The rate of my meters per second, can you see it took me shorter? And so the rate at which I was traveling changed. And that's what speed is. Speed is the rate at which I'm changing my distance per time. And so speed is actually the change in distance, and I'm going to just say distance for now, over the change in time, which we know from meters per second. We know that. But what do I know about this speed? Now, we're talking about speed as in scalars from grade 7. In other words, it doesn't have direction. It only has magnitude. So, I've got speed and I've got distance over time. What is this actually? This is the change in the y-axis. Yes, you are thinking exactly what I'm thinking. And this looks a lot like a formula. X-axis. This looks a lot like a formula for one of our favorite topics in math, gradients. And what is gradient? Gradient is the rate of change, or the change factor. This is the change factor. Okay, how much am I changing my distance per time? Over here, from here to here, I was stationary. Can you see there's no slope here? And if there's no slope here, no gradient, it means there's no change. There's no change in my distance from the origin, from home. I'm checking out those blue cranes, and they cute little birds and cool. So my gradient represents change in distance per time, and we know that already in our speed. So let's look at this. They'll put on this A, B, C, D, E, and they'll say F, and they'll say, what is happening at A? Well, I'm starting from home, or from the origin. Then I work out what my speed is from y over x, from my gradient between here and here, my average speed. Okay, because in real life we'll walk a little bit faster and a little bit slower and a little bit faster and a little bit slower. We're not robots yet, anyway. Then from B to C, my distance is constant. In other words, I haven't traveled any further from the origin. Then, can you see this one is steeper? The gradient, the steepness of the slope is steeper. That means I'm going faster. From C to D is faster than from A to B. So I'm walking faster because it took me 20 minutes to do 2Ks. The next 2 kilometers took me 15 minutes. It means I was walking faster to do for another 2 kilometers. Then time carried on. Time doesn't just drop out of the sky and just do nothing. So it's time carried on, but my distance stayed constant. I didn't go anywhere further. Then I walked at the same rate. Now, this is not in real life. You'll go faster and slower, which will be more of a curve. But we like to talk about constant speed at first. And again, this is a scalar. It doesn't have any direction. So this is a very important concept, this gradient concept. Very important concept. The gradient becomes, now, the speed. If I speed up, can you see my speed was greater than there? If in the journey over here I had sped up even more, okay, that's not quite possible to get there in like 3 minutes in 1 kilometer. Well, if you Usain Bolt, maybe not even. My gradient changed. And what's the change in the gradient in a distance time? Well, we looking towards changing our speed. And what's the change in speed? And this is the real question. What is it when we change speed? And if there's direction, what is it if we change velocity? And this is the real question we're asking. Okay, story time. Because everything in physics, especially to do with motion, is things in real life that we can picture. It's not yet starships at the speed of light and we're trying to figure out what's going on with spaceships going to Mars. Okay, it's real life. So these two are Hansel and Gretel. Hansel and Gretel. And what's the story of Hansel and Gretel? Just quickly, Hansel and Gretel were born and lived with a poor woodcutter, and they had to do some chores and things because they lived in a house close to the forest, but they had to do a few chores, and that was fine, but they didn't want to, and they just wanted to have fun, and so they left home, but on an adventure. But they're not wearing shoes. These are definitely Afrikaans kids. Not kidding. Afrikaans kids are really hard. They Chuck Norris on steroids. They can take the walking without shoes everywhere. It's good. That's where Dukas comes from. So Hansel and Gretel, and then they go off, but they leave. Do you remember the story? They leave breadcrumbs. They leave. They throw down some breadcrumbs. Now we're going to pretend the breadcrumbs are like our ticker tape timer. In other words, the breadcrumbs can show us what's happening with what distance they covered and how fast they were going. So I'm going to say that every second they dropped a breadcrumb. But let's pretend they're very big breadcrumbs so we can really see them. So every second they dropped a breadcrumb. A breadcrumb. A big breadcrumb so you can see. Because they needed to they needed to find their way back home when they went gallivanting in the forest. So they left breadcrumbs, and then they met this lady who wanted to cook them up for supper, and she had a house made of sweets and chocolates and all things that are nice, but at the end of the day you'll throw up because they're not really good for you on large scale. Okay, so every second they dropped a breadcrumb. So let's say, because we now are talking about velocity and things like that, so let's say that they are walking, skipping, jumping. So walking or skipping. In Afrikaans, the word for jumping is spring. That's where you get the springboks. The bookies, the buck that spring. Spring is actually the word for jump. So actually in English, springboks are actually jumping or jumping bucks. But they were coined first as springboks. Spring is jumping. So they were walking, they were skipping, they were jumping. They maybe ran a bit, jumping. They maybe ran a bit. They're kids. They like to play. So they are going and they're dropping breadcrumbs so they can find their way back home. I hope this crow is not going to eat those breadcrumbs. But do crows eat breadcrumbs or like little insects and things? Anyway, so they are walking, skipping, jumping, running. They're going east. Let's say they're going east because we got east or west. So let's go east. And the first breadcrumb was after a second. And let's say this is the first breadcrumb, and then after 1 second, let's make it 10 seconds. That's our ticker type is usually 10 seconds. 1 second, then 2 seconds, then 3 seconds, then 4 seconds, then 5 seconds, then 6 seconds, then 7 seconds, then let me quickly pause this and do this accurately. Okay, so they dropped some breadcrumbs, and at 0 seconds as they left, they dropped a breadcrumb, then they dropped another one. After every second, they dropped a breadcrumb. Now, can you, let's say that this is our reference point. This is like where their home was. And they walked along through the woods singing Heidi, Heidi. Nice old Afrikaans song. So they went through the woods, walking, skipping, jumping, doing whatever. Now, what can you tell me about their speed? Are they walking at a constant rate? Are they, now let's give some times to this, or some meters to this, right? And we say that between the first and the second breadcrumb is 0.5 meters. 0.5 meters. Okay, they were kind of strolling along. That's like half a step in a second. Then 1.5 meters between the first and the second. Then between the second and the third second, it was 2.5 meters. Okay, what's happening now? And then between the third second and the fourth second away from home, they went 3.5 meters. Then between these two time intervals, they went 4.5 meters. Then they went 5.5, 6.5, 7.5. They went 8.5 meters in a second. Yeah, What were they doing between each second? What do you think was happening between the first second and the 10th second? Yes, they were excited to get out the door. So, what did they do? Between these breadcrumbs were much larger intervals between the distances. And so what does that tell us? Describe the movement. Number one. Well, let's just say it. What's the movement of Hansel and Gretel at the beginning of their journey between 0 and 10 seconds? Well, you've got it. They were increasing their speed. So they were going at 0.5 meters per second, then 1.5, then 2.5, then 3.5, and they were increasing their speed. Okay, so let's set up a table to say what their time and what their correlating position was from home. Okay, so we want time, 1 to 10 seconds. Position, we went 0.5. They walked and skipped and jumped 0.5. And maybe one of these is accelerating more. Maybe if they're skipping, they're accelerating more. There's a change in speed. Cool. So I'm etching towards something. In 2 seconds, how far had they gone? Well, between the second and, well, the first breadcrumb was at 0. I should have put a 0 here, but anyway. Second breadcrumb was 0.5 away. Between the first second and the second second, they did 1.5, but they've already done 0.5, so 1.5 plus 0.5 is 2. So they did 2 meters. 2 meters plus 2.5, they did 4.5. Okay, 4.5 plus 3.5 is 8. And I'm going to quickly pause that and quickly do that for you. Okay, so they've done half of what Usain Bolt has done in 100 meters. He did, I think, 100 meters in 9 point something seconds. So he did half. They did, in 10 seconds, they did 50 meters, which is pretty impressive for little kids. I think they were jumping hopping, skipping, jumping at a very good rate. Okay, and rate, the word rate refers to something over time. You've got to remember that. Okay, so let's see what's happening in the story with Hansel and Gretel. So they're walking, skipping, jumping. They're very excited to go into the woods to see what's there. They haven't heard of Red Riding Hood and the wolf. They haven't heard about the wolf or the funny people who live and funny characters who live in the forest. They just think the world is full of glitz and glamour, sparkles and candy. Okay, cool. So now from that, what can we do? I can make I wonder if I should do it on A4 quad paper. Okay, so I've graphed my different positions. At 1 second, I'm going to be 0.5, and this is seconds 1, 2, 3, 4, 5, 7, 8, 9, 10. But I didn't want to draw a huge one, so I've got every 5 meters, because I needed to get to 50, and we don't want 50 centimeters on here. So at 1 I've got 0.5, at 2 I've got about 2 meters, at 3 I've got 4.5. That's almost 5. At 4 seconds I've got 8. That's about there. At 5 seconds I got 12.5. But in graphs like this, you want to be a little bit more accurate. But I do have 50 meters between these 2 points. So between the beginning and the end in 10 seconds. And these are the breadcrumbs that they dropped. In 6 seconds, they had gone this far. In 6 seconds, 18 meters. In 7 seconds, almost 25. In 8 seconds, or 32, so just over 30. In 9 seconds, we'd gone just over 40, 40.5, and in 10 seconds they had gone 50 meters away. Now, what shape does this give? It doesn't give a straight line. Now, if I have a distance, we're relating this a lot. If I've got distance time, in other words, meters over seconds, meters per second. If I've got distance time, what is my gradient if I've got a straight line? Well, my gradient is constantly increasing, and what does my gradient represent? Represents the vertical. This is vertical. Represents the change in my vertical over the change in my horizontal, which represents distance would be in meters, and time would be in seconds. So my change in my vertical over my change in my horizontal would be meters per second. And we know that this is speed. If it's to the east with Hansel and Gretel, it'll be, I'm just using east as an example. We could have used west or north or south, whatever. Not necessarily up or down yet. So speed meters per second. So what is this? And this is a very important concept. What does the gradient represent? It represents the vertical of the horizontal. What is the gradient of the distance time? Or if you've got magnitude with direction, velocity, displacement time, what does the gradient represent? It means the change in speed. Now, did this speed change at all? No, the speed was constant. Okay, if I have a straight line and the speed is going at, this looks like a 45-degree angle, which means this is going for one, so my speed is going at the same rate, well, pretty much the constant gradient. And so I've pretty much got a constant speed. I didn't suddenly remember the first one. I said, what if I quickly speed up over here, which is kind of impossible to speed up that much, but if I speed up over here, well, my speed changed between here and here. And we're getting to a very important point here, that the gradient of a distance time graph is the speed you're going to take, and the way to know this is that it's the vertical over the horizontal. That's what gradient is. It's the change in y over the change in x in terms of math. And you're going to take its units. As soon as you take its units, algebraically it's to the -1. If I make these positive, not bases, but if I make them whole bases, you're going to look at the units and see what the units are doing. As soon as you can see what the units are doing, you know what type of motion it is. I'm going to say that again. As soon as you can see what the units are doing in terms of vertical over horizontal, you can see what the type of motion. And we had different types of motion. If we're standing still, I've got constant distance from origin. I'm not moving. I've got, let's look at it again. I'm at the shops from here, from D to E. I'm at the shops. It's constant. Time is still moving. But am I moving? No, I'm not going anywhere further. So I've got constant distance. And if I've got constant distance, I'm not speeding up or slowing down. I'm not even traveling anywhere. Okay, so the different types of motion, we look at our units to see what kind of motion we have. And our units come from gradient, which is vertical over horizontal. Okay, but what is this guy telling us? Let's join these points. Now, this is not a straight line. in my distance time graph. This is not a straight line, it's a curve. And what do we call this curve? Well, certain curves, we can call them hyperbolic. This looks a little bit like my parabola. And even the fact that it's a parabola in terms of the units is giving something away. My parabola is in terms of x squares. What else is in terms of squares here? Yes, we're on the right path to find out what is happening with this. Because after speed, what if I map this speed, and I say, well, let's take a tangent or a gradient of this. But can I take the gradient of a parabola? Can I take the gradient of a parabola? No, because it's different at every single point. Can you see the gradient is gentler, 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 and it's almost zero here. Even if I take a curve like this, the gradient is zero here, now it's very steep. Now it's gentler, now it's completely steep. Now it's a bit gentler, and the gradient is different at every point over the curve. Okay, and we haven't gotten to grade 12 calculus yet, so and calculus helps us work out the gradients of curves. So what are we going to do? Well, we're going to take, let me pause this. If I take a circle, can I find the gradient at this point? Yes, I can. What is this called? When something touches at one point. It's called if something is tangible, it's touchable, you can see and touch it. If a tangent means it touches at one place. Touches at one place. Okay. Now, I want to see the slope or the gradient of this, but I can't exactly see it. It's not, the gradient isn't the same here as it is here, It's climbing higher and higher and higher and higher. So what do? I make a little triangle. I make a line like a tangent that touches it at that point. So say, for instance, I say, what is the gradient at 3 seconds? Well, I make a line that touches that point, and I take it back to here, and I say, okay, what is, now I quickly work this out. You'll say the change in y over the change in x. In other words, because the gradient, and we're going to try and find it at this little point. But we're going to take change in y over change in x over this little 2.5 second interval. So the change in y over the change in x, I think I said was between, we've got to see our calculations again. So my change in y, 5 seconds, 12.5. 12.5 to about, I think I said halfway between, let's just see. Okay, if I would have drawn this really, really, really accurately, like super accurately, in other words, 1 for 1. So 1 second here, 1 meter here, 2 seconds here, 2 meters here. I would have 7.5 on the y-axis, and I would have 2.5, meaning 3 minus 0.5 as the x-axis. But what we really want to get to is the change in y over the change in x in this curve. Okay, I was supposed to draw it accurately, but sorry. So the change in y over the change in x of this curve. Now the change in y, if I would have drawn it accurately, I could have said it was 7.5 meters. If I drew it accurately, in other words, 1 for 1, not 1 for 5, I could have seen easily that it was 7.5 over 2.5. And I really should have done that. Please actually draw this accurately so that you can find out what the speed is that Hansel and Gretel were going at 3 um, at 3 seconds and at 7 seconds. What were they going? What speed were they going at 3 seconds and at 7 seconds? At 3 seconds and at 7 seconds. What speed were they going at? Please draw this accurately, one for one. So you're going to have 50 centimeters. Oh, you're going to have over 2 A4 pages. Okay, and then you're going to take a little triangle and make a tangent to it. I wonder if we can just do it on graphing software. We could probably just do it on graphing software, but let's see. Okay, so what speed were they going at 3 seconds? What speed were they going at 7 seconds? Well, the answer is actually encapsulated in the breadcrumbs that they left. Answer is actually in the breadcrumbs that they left. So this is quite interesting. So 7.5 meters over 2.5 seconds would give you 3 meters per second at the 3rd second. That was their speed. Meters per second tells you its speed. That was the speed they were going. They were going for every meter 3 seconds. But when they got to here, when they got to 7 seconds, can you draw? See, I drew a tangent to this line, and my slope was the y was 10. In other words, the change in y. So my change was like 30 minus 20, and my change in y. So I said 30 minus 20. And then I took my change in x, and my change in x was pretty easy. It's like 0.5, so it'll be 8 minus 6.5, which gave me 1.5. This was actually drawn more accurately, the second the second part than the first, but probably because we had greater distance, I just kind of marked it off here as possibly 1, possibly 2. I didn't use a ruler. So that's why this one works out mathematically, but I didn't use exact measurements for all my dots here. But these were easier dots. So here we go, 8 minus 6.5. So change in y over change in x, I got 10 meters between 30 and 20. And I got 1.5 seconds between 8 and 6.5. So I made like this little triangle, and you say, well, what if I make this longer and I make it 8 to 6? Well, this is going to be under here then. So then you're going to have to go 30 minus 20, 30 minus 18. This would kind of be to 18. So you've got to draw it accurately. And this wasn't super accurate. I just drew it for the sake of the shape of the graph. I drew it for the sake of the shape. We need to find this shape. So what have I got? 10 divided by 1.5 is 7 meters per second. What is the general pattern? What are you starting to see here? And can you make guesses about what's going to happen? If I'm moving at 3 meters per second in the 3rd second, and by the 7th second I'm moving at 7 meters per second, what do you think I'll be moving at by the 10th second? I'll probably be moving at 10 meters per second. And can you see that there's a change in my gradients? There's a change in my gradients. Now, all of this is about gradient, which represents change, and there's a change in my change. And what do I call the change in my change? Well, what do I call the first change? I call it speed. What do I call the change in that change? You've got it. The change in the change from distance. So we got distance. And the change in the distance, the rate of the change of distance over time, is called speed. But what if my speed changes per time? So there's a change in my speed. What is that called? That's called acceleration. That's when you put the pedal to the metal. Acceleration, and you hope you don't get a speed ticket. Okay, acceleration. And just for the sake of knowing, what's the change in acceleration? Well, if you change your acceleration very quickly, your car might jerk or jolt. And we call the change in that acceleration, the change in the change of distance, we call that jerk or jolt. But we don't use jerk or jolt until university. We do that in university. In high school, we only do the change in speed, which is acceleration. Later on in university, we do the change in acceleration, which means your car is going to jerk or jolt. And if it jerks or jolts without you doing anything to it, please take it to a good mechanic, because there might be, well, some issues with maybe what could it be? Could be power, could be your electrical system, things like that. So changing acceleration, but we don't go into that in high school. We go into it in university. Okay, so this whole thing is about change. And if this gradient represents the change in distance over time, the change in distance over time, what is the change in that gradient called? The change in the change, because gradient is the change. But what if there's change in the change? Change in the change. Because the gradient's changing all the time. Dit verander. Verander. For other. We call it acceleration. So as soon as you have a graph, a distance, or even a displacement time graph that has a curve in it, it means that the speed is changing over every point. And if the speed is changing over every point, what are we doing? We are accelerating. We are accelerating. We are accelerating. So what were Hansel and Gretel doing? They were excited for their journey. And when you're excited, you go faster and faster and faster. That's what acceleration is. Faster and faster and faster and faster and faster. Okay? So, let's see. What was their acceleration between the 7th second, between the 7th and the 3rd second? Well, the acceleration, how do we work out acceleration? The change in the change of distance, or the change in speed. There's 2 degrees from here. From here there's 1 degree. Okay. Well, we say acceleration, you can see in this graph, we're going to take, if it was from 0, we could just take this number and we don't have to take away 0. But if we don't start at 0, we've got to say acceleration is the final velocity minus the initial velocity, minus the initial, where we started, so where we ended, where we started. But this is acceleration. This isn't even speed. But what was this number here? This was the speed. And the speed with direction is velocity. So this was the velocity east. Velocity. And it was going east. And this was the velocity. And it was going east. Because a vector has magnitude and direction. So the acceleration, the change in distance, or the change in velocity. Remember, velocity or speed is a change in distance. Because I can't just transport myself. We're not yet in Star Trek, where I can say, beam me up, Scotty. And something can store my data and then deliver me to Australia in 1 second or 5 seconds. So, my velocity's difference divided by my time's difference. In other words, if I draw a velocity graph, it'll be my y-axis over my x-axis, if this is velocity or speed over my time. And so, if I've got this happening in velocity over time, I've got change in velocity over time, which means I've got acceleration. And we're going to look at that now. These are very interesting. It's all about the change, and the gradient represents the change. What kind of gradient it is? Is it a curve or is it a straight line? So my acceleration would have been, well, what's my final velocity? 7 meters per second. What's my initial velocity? 3 meters per second. What's my time? 7 seconds. Minus my time at 3 seconds. Final time minus initial time. Which gives me 7 minus 3 is 4. 4 over 4 is it's just 1. So I'm going 1 meter per second. But velocity is meters per second. If I'm talking about divided by time, I'm going velocity is a meter per second. So the change per second, because this is per second. And what do I say per second? Well, let's see. Remember, the units are very important in understanding this. Divided by another second. Because this is a minus 1, it doesn't cross out. It becomes meters per second minus 2. And what do you notice about this 2? Later on, not now, I think in university, we're going to see this parabola happening, or even the hyperbolic function. But I'm going to see something over x. I'm also going to see some squares, but much later on. So meters per second squared, per second is the change in velocity, which is the change in distance. So it's 2 changes. You see, there are 2 changes in here. And that's 1 meters per second. This is per second. This is per another second, which is per second squared. So, and if you don't give a direction, they take half a mark or even a mark off. And you're going to have to say east, because acceleration is a vector quantity in physics. We accelerate in a certain direction. Okay, I'm liking this Hansel and Gretel thing. Now, I'm going to, for the sake of time, I'm going to quickly make a table. And we're going to look at the average velocity and the change in that velocity. Okay, so if I've got a table with my time in seconds, from 1 to 2 seconds. Now remember, when we take the average velocity, I'm going to, because this was a curve, I'm going to take like a tangent line which has a definite gradient, same gradient all over a line, the tangent, and I'm going to say the change in y over the change in x. So I'm going to get an average velocity of 0.5, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5, 7.5, 8.5. What can you tell me about Hansel and Gretel's change in their change in distance, or their change in velocity? What can you tell me? Again, they were excited. Now, what was the change? I have 1 meter per second. 1 meter per second change. 1 meter per second. 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 Change in velocity. And what is the change in velocity? It's meters per second over, in the x-axis, another second, which is meters per second, meters per second, which gives us acceleration. Check your units. Your units will tell you the story. And so what was Hansel and Gretel doing? Nothing you can do in real life, because you can't actually accelerate at an exact constant pace, unless they were Germanly engineered by a, I don't know, Mercedes-Benz or something company. The Hansel and Gretel is a very, very interesting story, backstory to them. So they're changing all the time by 1 meter per second, by 1 meter per second. So what is the acceleration? The acceleration is 1 meter per second east. And that's the change. The change in velocity is acceleration. The change in velocity is acceleration. It is acceleration. But now we see, okay, cool. We've looked at a few different things. So 1 meter per second, 1 meter per second, 1 meter per second, we're going at constant acceleration. And we, in high school, we don't do anything but constant acceleration. We don't talk about jolt and jerk. So we always go constant acceleration in high school. Okay, so we're going constant acceleration of 1 meter per second squared to the east. Okay, now instantaneous velocity is an interesting thing, because it means the velocity increases in 1 meter per second. So accelerates from rest. The initial velocity they had was 0 meters per second, and then it increased by 1 meter per second. So its instantaneous velocity is going to be 1 per 1 per 1. So 7 meters per second. Check out what instantaneous velocity is. If I go from A to B to C, and I say the instantaneous velocity between A and C, I'm going to choose its midpoint to find instantaneous. That means, like on a curve, you see I did the midpoint of that, and then I said, well, the change in y over the change in x over that y distance by that x distance. And we'll speak about that in another video. But that's instantaneous velocities. Jumping springboks. Let's not take it all out. Okay, so what if I draw a velocity time graph of Hansel and Gretel's ticker tape timer, or their breadcrumbs that they left? So the distance is changing, which becomes the velocity, and the average velocity, it changes at the same rate, which becomes acceleration. But how do I draw this? Well, let's see. At 2 seconds, they were going at 2 meters per second. Do you remember? At 4, from this, 2. At 4 seconds, they were going at 4 meters per second. Remember, we're increasing 1 meter per second at a time. And that tells us something. So the change is 1 meter per second in velocity. It's the rate of change. Rate means over time. Okay, so the rate of change of velocity at 1 meter per second would actually be acceleration. So let's look at what this is. So I've got at 5, at 6, let's just do this in 2s quite easily. At 6, at 8 seconds, we're going 8 meters per second. At 9, at 10, we're going 10 meters per second. And what can you see here? Okay, pretend I do this really well. And pretend those dots are perfect. What can you see here? This is a perfectly straight line. This is a perfectly, what's supposed to be perfectly dotted there. This is a perfectly straight line for our Hansel and Gretel. So velocity of Hansel and Gretel. Oh, she wants a capital letter. Velocity of Hansel and Gretel. Velocity of Hansel and Gretel is increasing at a steady rate. And if there's a change in velocity, what do we call that change? Well, let's look at our units again. I don't know, I've said it a few times, but we've got to look at it every angle. So if I have meters per second, and I'm dividing that by time, remember, to get the gradient is the key word in all of this. The gradient or the slope tells the story of their excitement. And the gradient and the slope will tell the story of what's happening in your motion. Am I staying in one place at the mall? I've got a constant distance over time. Am I speeding up? I've got a change in my distance, the rate of distance over time. Am I speeding up my speed? I've got acceleration. So the gradient tells us the story. So what's happening with this? The gradient is the change in the y-axis over the change in the x-axis. And the change in the y-axis is going to be meters per second, to the -1, over time, which will give me meters per second -2, which is acceleration. And acceleration is the change of distance. So what we really want to know, well, how far did they go? How far did they go? Well, you say to me, but we know we went 50 meters in 10 seconds. We covered 50 meters. But at a different point, if I ask you at 4 seconds, how far did they travel at 4 seconds? How far did they travel at 4 seconds? So at this 4-second mark, how far did they travel? So, and I'm going to take something a little bit more interesting, a little bit different. Say, for instance, I was going at a constant speed. I'm going to say speed for a reason. Speed over time. And I'm going at a constant speed of 10 meters per second. I'm going at a constant speed of 10 meters per second. What have I done? Constant speed looks like this. There's no change. The word constant says there's no change in this. Although there's change in distance, there isn't a change in speed. So I'm constantly at 10 meters per second. In the first second, how much will I do? 10 meters. In the second, how much will I do? An extra 10 meters, so I would have done 20 meters. In the third second, how much will I do? Well, I would have done 30 meters. In the fourth second, and you can see I can go on like this forever. But how can we get to the distance without dividing it up into many, many, many little blocks? Well, what is area? Area is length. Remember, this is 10. I said 10 times 1 is 10. 10 times 2, 2 is 20. 10 times 3 is 30. 10 times 4 is 40. So I went 40 meters. I can tell the distance by saying length times breadth, or what was length times breadth? It's really the squares inside, all the squares inside this, which refers mathematically to our understanding of area, which is measured in squares. So our area is measured in squares, and it's the length times the breadth will give you the distance that you went. For 10 meters per second, I went for 1 second, for 2 seconds, for 3 seconds, for 4 seconds. This is how I find my distance from my velocity graph. This is how I find my distance that I've traveled from my velocity graph. Okay, so if I say 10 meters per second, and I times by seconds, please get the units, these units, length, this is the length, or breadth, whatever you want to call it. Let's pretend this is length for now. This is the length times the breadth times this. Meters per second times seconds. What's meters per second times seconds? Well, let's see. Meters per second times second is actually meters per second times seconds over 1. Can you see that gives me my meters? So always look at your units. Your units will tell you where you're going. Now I've gone back to just meters by timesing the y-axis by the x-axis. So when I say length times breadth, I'm saying meters per second times seconds, because this is the x-axis in time in seconds. So I say meters per second times seconds gives me meters again. So if I want, in the same way, if I want to work out how far I went in 4 seconds, guess what? What's the area of a triangle? Because the triangle is half of that. Well, half, well, not quite the rectangle, half of it square, but anyway. Half base times height, and it's perpendicular height. And so I'm going half times base is 4. Now you can choose either one, because 4 times 3 is the same as 3 times 4. Okay, so half base times height, half 4 times 4. And 4 times 4 is 16, half of that is 8. So I went 8 meters. Oh, sorry, Hansel and Gretel traveled 8 meters in the first 4 seconds. So you could see they were speeding up, because then they did 50 meters in 10 seconds, which is not additive. It is slightly exponential. It's, yes. So 8 meters in the first 4 seconds. So you can find area by timesing length times breadth. Find the area to go back 1, to cancel out one of these S's, to go back to distance. In the same way, you can find velocity in your acceleration graph. If I got a constant acceleration, I can find the velocity, because I've got meters per second minus 2 divided by seconds here, which would go back by seconds, which would go back to giving me meters per second, which would go back to the velocity. And the velocity, like this, back to the distance. So you can work it out at any point. Work it out at any point. So area under the graph between 0 and 4 seconds, which is half seconds times meters per second, which is 8 meters. And that's their displacement from home. So, and the story carries on, and they I think they pushed the witch into the fire or something when she's trying to cook them. But that's just another story. But all of this, the gradient of every graph tells us the story of what's happening with Hansel and Gretel. So the slope of the velocity time graph gives us acceleration. The slope of the velocity time graph gives us acceleration. The slope of the distance times graph gives us velocity. They're degrees of change from one another. And if you want to give Hansel and Gretel a different story ending, maybe they meet Red Riding Hood or the wolf in the woods, that would be quite exciting. Let me know. Okay. Good job.